In this video, I'm going to be talking about PID controllers. I'll explain what P, I, and D stand for in a minute, but first let's get a sense for the problem that we're trying to solve. So this class is about writing programs that control robots. Presumably you have a lot of experience writing programs. So for example, if I were to ask you to implement a method that would work like this, person.setName Alice, that's just setting the attribute, the value of some attribute of this person object, you wouldn't have any problem writing that code. It would just take a couple of instructions, and when we execute that code, it would execute almost instantaneously. That's fairly different from the situation where we're writing a robot control library and we want to actually change the physical state of a robot. So for example, let's say we have a robot with an articulated arm, and we want a method that will change the angle of one of the joints in that arm. Elbow.setAngle 45 degrees. So what's going to have to happen under the hood in order for this statement to execute is very different from what's happening when this statement executes, even though on the face of it they look similar. So for one thing, this is necessarily going to take a long time to do what needs to be done. In order to physically change the state of the robot, in order to move that joint, well, that's going to take milliseconds or even seconds to complete, which from the point of view of computation is an eternity. Also, if this is going to work reliably, the algorithm underneath this method, the code that we're going to have to write, will necessarily be a little bit complicated. So if you think about what has to happen, we'll need to probably send some voltage to a motor over some period of time. Maybe we're going to try to determine in advance how long we have to make that motor turn. Maybe we're going to monitor the angle and continue moving until we reach the desired position. Regardless, it's going to be an operation that's going to take time to complete. Also, there are likely to be external circumstances that are going to change what has to be done by this code. So for example, if we imagine that the configuration of the arm is such that changing this angle is going to move the arm up, it's going to take more torque or more voltage to move the arm to overcome the force of gravity. Similarly, if that arm is carrying some sort of heavy object, we're going to have to apply even more torque or more voltage to move the arm. So that's really what this video is about. If we need to write code to reliably change the state of a physical system, of a robot, how can we go about doing that? So an articulated arm or a robot with limbs is a sort of complicated system. So for the purposes of this video, we're going to think about a simpler system. So we're going to be looking at this autonomous locomotive. And a train is a nice system to think about because it's inherently one-dimensional, right? There's only one degree of freedom here. The robot can move forward or backwards along that track, but that's all it can do. So here we've got the notation that we're going to use to describe this system. So x of t, we'll use that to denote the state of the locomotive at time t, the configuration of the locomotive at time t. And in this case, that's just referring to its position along the tracks. G of t will be used to denote the goal configuration. So that's where we want the robot to end up. And E of t is going to express the error, right? And that's just the difference between those two. So E of t is just the goal minus the current state. And all of these are functions of time. So where this t is expressing the idea that the configuration of state is going to change over time. The error is expressing the error at a particular time, and presumably this goal location could also change over time. So this is a pretty general kind of control problem. People have put a lot of thought into how to address this. So what should we do to send a control signal to this locomotive to drive that error down to 0? And you could take an entire semester-long class looking at different approaches to this problem. So we're going to look at one particularly simple but widely used method for addressing this in this video, which is PID controllers. And we're going to start with the simplest possible approach, or a very simple approach, proportional control. And I think proportional control is a pretty intuitive and simple way of thinking about this problem. So the idea is that we're going to monitor our error, and the amount of control that we're going to apply is going to be proportional to the current amount of error. So if we have a large amount of error, we're going to apply a large control signal. If we have a small amount of error, then we'll only apply a small amount of control. Which I think makes sense if we think back to our locomotive example. So if we imagine that the locomotive is almost at its goal location, it seems to make sense that we shouldn't need to apply a lot of force to get it to cover that last small amount of distance. Whereas if the locomotive is far from the goal, it seems to make sense that we should apply a larger control signal. And I keep saying control signal, right? So that's going to be denoted with this U of t. That U is going to describe whatever our control variable is. So that will be different things under different circumstances. So in our original example of the robot control arm, that might be the amount of voltage that we send to that motor. In the case of this autonomous locomotive, that might be the angle of some sort of throttle lever that we can use to accelerate the locomotive either forward or backwards. So exactly what that represents is going to depend on the system that we're controlling. It's got to be something that is a scalar value that is going to push the system in one direction or another depending on the magnitude of that value. So this is our proportional control formula, and it expresses one really simple way of selecting what that control signal should be on the basis of our error. The only thing we haven't explained yet is this k sub p. That's called a gain term. So that's a fixed parameter that we're going to have to select in order to make this thing work. And basically, that's just telling us, for a particular amount of error, what should the control value be? We're just going to multiply these two things together. So if I increase that gain term, I'm going to have a more aggressive controller that's going to apply more control signal for the same error. And in general, we're going to have to select that experimentally. That's something we'll just have to tune by trying different values and seeing what gives us the behavior we want. So this is our formula for proportional control, but remember what we're really trying to do is figure out how to write the code to make this happen. So let's look at how we can implement this as Python pseudocode. So here's a Python function that takes 3 arguments. This train object allows us to access the current state of the train, its current position, and it has a throttle method that allows us to send this control signal to basically position that throttle lever. This function also takes the goal position that we're trying to reach and this gain parameter. So the code itself is pretty simple. We have an infinite loop, and inside that loop we repeat 3 steps. First, we calculate the current error by looking at the goal and comparing it to the current position of the train, so the difference between the two is the error. Then we calculate our control value by multiplying that gain term times that error, and then we pass that control value to the train, causing it to move. And then we repeat. We again check the position of the train, which presumably has been updated. The train's moved a little bit. We get a new error term. We get a new control signal. We apply that new throttle value. And we loop, and we do it again, and we repeat this process indefinitely. So this is an example of closed loop control. Closed loop control means that we check the state of the system, we adjust our control based on that state, and then we repeat indefinitely. That's in contrast to open loop control, where we look at the initial state of the system, we look at the goal, we figure out what control we want to apply, and then we just do it without repeatedly checking the state of the system over time. Sometimes that's necessary. Closed loop control tends to be a little bit more robust because we're responding to the state of the system as it's changing. Let's see what happens if we apply this controller to a simulator for that locomotive system that we saw before. So this looks a little bit complicated. Give me a second to unpack what's happening here. The y-axis here is showing the error value. So that's that difference between the current location and the goal location. So you can see that here we're starting at an error of 1, And what that means is that we're starting 1 meter in this case from the goal. So if we look at our train here, maybe the situation is that the train is at 9.0, the goal is at 10.0, and we subtract those two, and we get 1. So what will our controller do under these circumstances? Well, if the error is 1, and my proportional gain term here is 10, I'll multiply those two things together. I get 10, and that's where I'll set that throttle. That's the amount of force that I'll apply to the system. And presumably that's going to move the train forward. And in fact, that's what happens. If we look at time moving forward, over time, our locomotive is moving down toward the goal, or moving forward toward the goal. And eventually, this is good news, we reach the goal. This is what we wanted to happen. So at this point, the error is 0, and the locomotive is at that target location. And if you think about what the controller is doing at this point, well, the error is 0, so 0 times our gain is 0. We've basically taken our foot off the gas. We're not applying any force to the locomotive. So unfortunately, what happens next is that it keeps moving. And if you think about locomotives, that makes a lot of sense, right? They're very heavy. Once you get that thing up to speed, just taking your foot off the gas doesn't stop it immediately. In this case, it's going to just keep moving and overshoot the goal. That's a problem. So maybe the good news is that our controller is still operating. So once it goes past the goal, now we have that error term becomes negative, meaning that the control signal that we pass in is going to become negative. So basically we're going to move that control throttle, that control lever back, and we're going to start driving the train backwards, back to the goal position. So that slows down the train. Eventually it stops the train starts moving backwards to the goal, and aha, excellent, it gets back to that goal location, but by that time it's picked up enough speed going backwards that it will overshoot again. And then this process will repeat indefinitely. So in the absence of friction, that train is just going to oscillate back and forth forever. And you might think, well, no problem, I'll just crank up that gain term. So here's what happens if we do that. Now we're pushing harder, right? We're applying more of a control signal for that same error, which means that we get to the goal faster. But of course, at that point, we're moving faster when we get to the goal. And so the result is that we see these oscillations, we still see these oscillations, we've just changed the period, we've just shortened the period. So we need to do something different. And in general, proportional control is fine sometimes. It's fine in systems without momentum. If our control signal is able to just directly modify the state of the system without these other issues showing their face, then we may be okay with a pure proportional controller. But here we're dealing with momentum. We might also have issues of friction. We might also be working against outside forces. So if we are in this kind of situation, we're going to have to do something else. The first thing we're going to try is to introduce a derivative term. So this is the D in PID control. And the intuition is that where our original proportional controller was just looking at the current error, this new version of the controller is going to look at the current error, but it's also going to look at the rate of change in the error. So if the error is going down, then that means we're already moving toward the goal and we can ease off on the control signal. If the error is going up, in spite of what we're doing with our controller, then that's an indication that what we're doing isn't working and we need to increase the control signal. So that's the basic idea, that's the basic motivation behind this derivative term. So in order to make this work, we need to actually have access to this derivative. That's not something we're going to have access to directly. We're going to have to calculate that or estimate that. So let's think about how we might go about doing that. One thing to keep in mind is that when we're working with a control system, when we're trying to write code to control some system, although we might be expressing our control rules here mathematically and continuously, we're actually working with the discrete time system generally, right? So our controller is going to be getting readings from the system, the position of the locomotive, at some fixed time intervals, maybe 10 times per second. And similarly, we'll be sending our control signals maybe 10 times per second. So it's not really a continuous function, or we don't have access to a continuous version of that information. So that might look like this. right? We have an error that we calculate at this point, and then sometime later, after some delta t, we get another estimate of the error, and then sometime later we get another estimate of the error. So presumably underneath there is some actual position that's changing continuously over the time, but we get readings at discrete time intervals. So the goal is, in order to make this work, to calculate the derivative of this curve at these points, because we're going to need that in order to calculate this derivative term. We don't have access to that directly. The easiest way to estimate it is just to look at two subsequent points and estimate the derivative to be just the slope between those 2 points. And that's what's being expressed here. So how can I find the slope between those 2 points? I can look at the difference in the magnitude of the error between those 2 points. So that's this number. That's this there. And then I can look at the delta t, the time delay between the 2 points. And I can calculate the slope between the two as this difference over that time delay. The rise over the run gives me that slope. And that's an estimate of the true derivative at that point. And it's probably a good enough estimate. It doesn't have to be perfect. Although one thing we have to be careful of is the situation where we have noisy estimates of the state. So in that case, we might end up seeing readings that look like this. So the underlying state of the system might be something like this. But we're getting noisy estimates. We're getting noisy readings from some sort of sensor. And if we use those noisy readings to estimate the derivative over time, what we're going to see is a derivative that looks like this on this time step, like this on this time step, a large positive derivative, then a large negative derivative, then a large positive derivative. So the derivative is going to be bouncing around like crazy, and that's going to make our controller behave erratically. So that's just something to be careful of. So again, we need to figure out how to implement this. Here's an updated version of our controller pseudocode that includes that derivative term. Now I need to keep track of the error from the previous time step. That's what's happening here. As well as the error from the current time step, so that I can take the difference between the two to estimate that derivative. And that's what's happening here. Once I've estimated that derivative, then I can calculate my control signal as the sum of these two quantities, right? Here's my original proportional controller, and here's the derivative term. And again, I make these calculations in a nice tight closed loop. So let's see what happens when we update our controller for our locomotive. So what do we see here? We have 3 different curves. Each of these curves we're using the same proportional gain term, but we're experimenting with different amounts of derivative gain. So let's, for a second, focus on this first one, the gain of 5 for the derivative gain. And that's going to lead to this red curve. So what we're seeing here is we're not really applying enough, the gain isn't high enough on the derivative term here. We're still seeing those oscillations. But it's better than what we had before. Those oscillations at least are getting smaller over time. So why are they getting smaller? Well, if you think in this case about now what's happening when we get to 0 error, well, at this point, the proportional term is 0. Our proportional part of the controller isn't telling us to do anything. But the derivative part is recognizing the fact that the derivative here is negative, which means that we should actually be pulling back on the throttle, right? So as we're passing the goal position, we're already pulling back on the throttle, trying to correct that. And if we follow that logic, we end up damping that oscillation. But we didn't do it. 5 doesn't seem to be quite enough. So now we try 20, and that gives us our magenta curve here. And that looks pretty good. We still overshoot a little bit, but we pretty quickly correct and we settle in on the goal after about 3 seconds. So we did overshoot a little bit, so if we're really concerned about not overshooting at all, we can try turning the gain term way up. So here's what happens when we turn it all the way up to 60. We get this blue curve, and here we're not overshooting, but it's taking us a long time to reach the goal. Now why is that? as soon as we start to pick up speed toward the goal, as soon as our derivative of the error going down gets a large negative value, then that causes us to pull back on the throttle and slow down. So here we have the proportional term and the derivative term essentially acting against each other, so that it's taking a long time for the train to reach its goal position. So when I said earlier that we have to tune these, that's what I meant. We have to experiment with different values here until we get this curve sort of look the way we want it to. So that's working pretty well. Let's look at this situation and see how we're going to handle that. So here, it's basically the same scenario. We have a locomotive. It's trying to work its way to this goal configuration. But now we're moving uphill. And that means that we're moving against the force of gravity. So what will happen if we apply our proportional derivative controller to this system? This is what we'll see. So these are the same gain terms we had before. And if you look at the curve, this magenta curve, qualitatively it looks pretty similar, except it's not actually settling at the goal location. Well, why not? So if you think about what's happening here, the train is stopping maybe there, and at this point, there's a certain amount of error, so there's a certain amount of acceleration being applied, or force being applied by our proportional term, pushing the train in this direction. This point where the train stops is where that force is exactly counterbalanced by the force of gravity pushing the train down the hill. So if we were to move the train a little bit forward, it would reduce the amount of force that's pushing the train up the hill, and then gravity would push it back down. If we move the train a little bit backwards, well, then the proportional controller would push harder, overcoming the force of gravity. So this is that equilibrium point where they're in balance. And once they've balanced out, right, our derivative term isn't doing anything because the error isn't changing, so that's zero. So this effect, this phenomena, is called droop, sometimes referred to as droop. And this happens when our controller is acting against some external force. So how can we deal with that? Well, as you may have guessed, it's going to have something to do with an I. We're going to introduce one more term in our controller, the integral term. And where the derivative term was sort of looking forward in time, it was looking at how fast the error is going down in order to decide what to do. We can think of our integral term as looking backwards in time. And the intuition is that if there's been a lot of error in the past, we must not be applying enough control signal, so we're going to increase the control signal. And we're going to recognize that by calculating the integral from 0 to the current time of that error value, of that error signal that we've been seeing. So looking back at this figure, what that means here, if I'm interested in the value of that integral term, say at this point, that's going to be the error under this curve from the beginning of time up until that point. And as you can see, if I don't drive that error down to 0, the area of this area under the curve is going to keep increasing indefinitely. So eventually, if I'm including that in my controller, I'm going to push harder and harder over time until eventually I do drive that error to 0. So that's the idea behind this integral term. And again, this is expressed continuously, but I'm going to have to be working with discrete quantities. So whenever I have an integral, and I need to calculate, and I need a discrete approximation of that integral, that's always going to become a summation. So here I'm summing up across all of the time steps where I've received information. So from time step 0, and here's assuming I have a constant delta t, the same amount of time between each time step. So the current time divided by delta t tells me the total number of time steps that I've completed, and I'm summing up my error at each of those time steps. And I'm multiplying that by the delta t to give me the area under each of those little regions as an approximation of the area under that curve. So what does that look like in code? This is starting to look a little bit complicated, but I'm just adding a couple of lines relative to what we had before. I need now a variable to track that summation, where I'm accumulating that error over time, and then in each time step I need to update that by looking at the current error, multiplying it by my delta t, and adding that to my sum. And now my final control signal is based on those three quantities. So what happens when I apply this controller to my locomotive? This is what happens. So here we've got the same proportional gain that we've been looking at, we've got the same derivative gain that worked well before, and I've added in this integral gain. And where did I come up with 40? Well, I just played around with it to pick a value that seemed to work reasonably well. And what we're seeing in this figure is all of these different curves are those same three gain terms. What's changing is the slope of the hill, the steepness of that hill. So here's a fairly gradual slope, only 5 degrees, and here's a fairly steep slope. The train is trying to go up a 15-degree incline. And the good news is that regardless of the slope, the locomotive is able to move to the goal location without droop, right? There's no gap here between the final position of the train, or the position of the train after 5 seconds, and the goal location. So we've fixed the oscillations with my derivative term, we've fixed the droop with the integral term, and the proportional term is actually pushing the system toward the goal. So that's a PID controller.